because you have some problem of internet services at your place. But now, since you are in the hostels, there should not be any such problem. Okay, so if we have a vector, okay, so that this is equals to 0, that is u is an eigenvector. Okay, and then we said that we can actually write something like this of v equals to u. Okay. And whether such a system, what we wrote on in the second line, as a solution. So this is a question. Just 1 minute, let me put my phone off. So we saw some examples, a 2x2 system, and also we saw a 3x3 systems of different cases. That is, geometric multiplicity is 1 less than the algebraic multiplicity, and geometric multiplicity is 2 less than the algebraic multiplicity. In both the cases, we were able to find the vectors that are required to produce linearly independent solutions, and they are involved in constructing a solution of this type. Okay, and also the A minus lambda I into W equals to. What are these equations, and why such equations will have a solution? Okay. And when do we have a solutions for this, right? Is it always this kind of things? I can keep on writing these things and there will be a series of vectors, non-trivial vectors, or it has something to do with geometric multiplicity. So this is a natural question that one asks. Okay, and this is one, and other one is, if you recall the first order equations, we call y prime equals to ay, okay, and say y at 0 equals to 1. Then we call we wrote the solution y equals to exponential. So if A is now a matrix, so they have a, right, that is the system. Then can I write the solution of the system? Okay, please mute yourself, all of you. Okay, already found a solution y. Can we call something this like this as exponential of a matrix times t? Can this be, does it make sense? Okay, because here you have from the calculus, you write this as 1 plus a into t plus, right, t square by 2 and so on, an infinite series. Then what will be this here? Can I, because this one will make sense for me, right? The right hand side things make sense to me, right? because given a matrix, you can keep on writing this a square, a cube. Therefore, I can write a matrix equation like this. So, can I call such a thing as an exponential? And if I call, that means, let me repeat, if I take a matrix A, if it converges in some sense, whatever the sense that we wanted, if it converges, say uniform, right? Then can we call that as something like this, exponential of A into T? And even if we call it, will it have any relation to AY? That means we are now mixing two things. One is that one thing that is coming from the calculus, and one thing which is coming from the, these are the things which are coming from the calculus, and here these are the things coming from the differential equations. Okay, so whether these two things, are they one and the same, or they are two different things? Okay, so these are the questions that we want to answer. After this is provided by the Jordan canonical form. Okay. So therefore, what we see here is that what we study in the calculus, what we study in the differential equations, what we study in the linear algebra, they are not going to lead us to three different things. They are going to lead us to only one theory. Okay, only that we are not able to see. But once we learn more deep into this, then we can see that all these things are actually leading to only one concept. Okay. So this reminds me of again Shankaracharya's Advaita. Okay. All the things that what we take, we see them as different at some stage, but when you look more deep into the philosophy of that, they are one and the same. Okay, so let me introduce one by one the concepts here. We know what is an eigenvector, right? So given a matrix A, which is of n and by n matrix, we call a non-trivial vector, okay, non-trivial vector, is called generalized eigenvector. It's called generalized eigenvector. If minus k u equals to 0, because the smallest such k is called the index of the eigenvector. Okay, eigenvectors I'm calling for corresponding to the eigenvalue lambda. Okay. Lambda is fixed, one I for the corresponding to, you have lambda is a scalar, and if such a thing is true, then we call this UR is a generalized eigenvector. Say for k equals to 1, okay, that is is 0. Right? So that means U is an eigenvector. Is an eigenvector. That is the generalized eigenvector of index 1 is an eigenvector. It is generalized eigenvector of index 1 is called is the eigenvector, not called, is the eigenvector. Is the eigenvector. So the 1, 2 is Vk is a generalized eigenvector. Eigenvector of index -1. Okay, defines. We are defining Vk minus 1. How do I define Vk minus 1? Is nothing but a minus lambda I generalized eigenvectors of index 9, index 8, index 7, like this. Okay. Why is that? This is because, why is this? This is because a, okay, for k minus 1 of Vk minus 1. This what we have to show that this is equals to 0, right? And k minus 1 is the smallest such thing. These are the two things. So what is Vk minus 1? If I substitute what is Vk minus 1, I get k Vk. And I know that Vk is a generalized eigenvector of index k. Therefore, this is going to be 0. And k minus 1 is the smallest because if I write a minus lambda I, okay, over k minus 2 into Vk minus 1, that is going to be simply a minus over k minus 1, right, of Vk. And this is non-zero because Vk is an eigenvector generalized reference k. Therefore, k is the smallest where this is 0. So this is non-zero. K is the smallest vector where minus lambda I power k Vk is 0. So therefore, power k minus 1 Vk is non-zero. Okay, this therefore follows that. Indeed, this is the explanation why this Vk minus 1 is an eigenvector of index k minus 1. Okay, so therefore, what we have is that V1 will be a minus lambda I of V2, and that is nothing but a minus lambda I square of V3, and so on. Okay. So what we earlier spoke about in the first page, what I said, I looked at this equation, right? So that is, this is U is an eigenvector that is a generalized eigenvector of index 1. So what we are asking is V is generalized eigenvector of index 1, index 2, right? This is a generalized eigenvector of index 2. That's what I wrote in the last line. U is going to that. So W is a generalized eigenvector.
Sir, your voice is breaking.
Is it because of the internet, or it's breaking for everyone, or only for few?
Yes, sir,
Yes,
it's
Yes,
breaking.
sir. Yes, sir. It's break.
sometimes. Yes. The internet is okay. So what I was saying is that these vectors that we were looking at. Okay, so recall we were looking at a minus lambda I times u equals to 0, and a minus lambda I okay. This is the kind of thing we were looking at. So if I take one more time in this equation, okay, so what this is equivalent to, writing a minus lambda I square of v is a minus lambda I times u, which is 0. So that means it satisfies this equation, and for less than 1, that's this is true. Therefore, v is generalized eigenvector, okay, of index. Okay, so we are looking at, in fact, is the solution of differential equation. Okay, existence of generalized eigenvectors. So how many such eigenvectors does a matrix have? Generalized eigenvectors. Okay, so similarly, the other one is going to be a minus lambda I. W is to v. So this also you can see that this is same as a minus lambda I cube. Okay, so take one w I, so t minus lambda I of v, that is going to be u, and therefore you have to take one 0. So this becomes 0. Okay, so that is v is again w is generalized eigenvector of index 3. So this is how we are formulating our does this eigenvectors, generalized eigenvectors, exist, and if they exist, how they will look. So first thing is, if there are generalized eigenvectors, they are going to be linearly. So that is the first we will prove. Okay. So suppose we have v1, v2, yeah, are generalized eigenvectors, okay, of an n by n matrix. Of n by n matrix. Then they are linearly independent. They are linearly. So I will do the proof for n equals 2, and all other things can be done similarly. Okay, I'll just do for n equals 2. So we assume that u let me write v1 equals to u and v2 equals to v are generalized eigenvector. Then write c1 u plus c2v equals to 0. So for linearly independence, we have to show that c1 and c2 both of them are 0, right? And what we have that v is generalized eigenvector. U and v are generalized eigenvectors, means that u is let me write in all generalized eigenvectors of index 1 and 2, of index 1 and 2 respective. So that is the V is the generalized eigenvectors of index. Generalized eigenvector of index 2. It is V satisfies okay A minus lambda I to V equals to. Therefore, plug in this in this relation. Okay, so you get U is A minus lambda I okay into V and C1 plus so and apply the operator A minus lambda I once again. Apply the A minus lambda I once again. Then we get C1 A minus lambda I square into V plus C2 A minus lambda I V equals to 0. And we know that this is 0, okay, because V is a generalized eigenvector of index 2. Okay, so therefore C2 into A minus lambda I V is 0. And we know that this is non-zero because that is nothing but U. U is a eigenvector, therefore it is not true. So this implies C2 is 0. Okay, so this implies C1 U is 0 and U is non-trivial, implies C1 is also 0. So we get C1, C2 both of them as 0. So if they are V1, V2, V1 are generalized eigenvectors of index 1 to okay, so now comes to the existence. Any questions?
सर थोड़ा तेज बोलो, आपकी आवाज कम आ रही है.
आवाज कम आ रही है?
यस सर, मतलब ईयरफोन में सुनाई कम दे रहा है.
And sir, there is a lot buffering also.
Yes,
There is
the
Yes,
breaking
sir.
also. So break हो रही है आवाज आपकी sir.
Yes.
बहुत ज़्यादा sir.
I can only speak normally because if I keep shouting, then that won't be continuous. It will be. Okay, so let us look at the existence of a generalized eigenvector. So again, we'll take n equals to 2. Okay, the same thing will we can once we understand this, then the same thing happens for any general n. In this case, if lambda is repeated eigenvalue, okay, and geometry lambda of lambda not equal to
So your voice is breaking a lot, sir.
change my network. Wait a minute. Okay, so I changed the network to my mobile. So let's see how it. So can you see my screen now? There's no disturbance, right?
Yes, sir. We can.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So if lambda is a repeated eigenvalue and geometric multiplicity of lambda is not equals to algebraic multiplicity. Okay. So that means there is only one eigenvector corresponding to the eigenvalue lambda. then there exists a generalized eigenvector of index 2. Okay, see here, there is no eigenvector, secondly independent eigenvector in this case. That gap is filled by the generalized eigenvector, and we already proved that this generalized eigenvector is going to be linearly independent from the eigenvector. Okay, so how does this come? Let us look at a proof. This explains the importance of the geometric multiplicity being strictly less than the algebraic multiplicity for the existence of generalized eigenvector. Okay, so let me take it is taken 1 and 2. So you know by Cayley-Hamilton theorem, I guess all of you know what is Cayley-Hamilton theorem, and that tells us that a minus lambda I square is going to be 0. A minus lambda I square is going to be 0. That means the kernel or null space of A minus lambda I is of dimension 2. Okay, so the kernel of this is going to be 2. I don't know how you denote it, but what I mean is the dimension of the null space of A minus lambda I square is going to be 2. Okay, our kernel is of dimension 2. And what we have from the hypothesis is that the kernel of A minus lambda I is 1. That is because it has only one eigenvector. It is because it has only eigenvector. Only one eigenvector is there. From the hypothesis. Okay, so A minus lambda is 1, the dimension of this, and the dimension of kernel of A minus lambda square is 2. So that means you can find one vector which is in A minus lambda is null space of A minus lambda square, which is not in the null space of A minus lambda. Right? So that is what we have is A minus lambda I, which is going to be contained in this but not equal kernel of A minus lambda I square. Therefore, there exists one vector z which is in the kernel of A minus lambda I square. Okay, and z is not in this, in the first one. Okay, so that is, it is in the kernel of A minus lambda I square means A minus lambda I into A minus lambda I z is going to be 0. So call this as, what should be this? This is this vector belongs to the kernel of A minus lambda I. This belongs to the kernel of A minus lambda I. Right? So this belongs to the eigenspace of lambda. Eigenspace of lambda. And we assume that it has only one eigenvector. Lambda has only one eigenvector. Therefore, A minus lambda I into is equals to, maybe it can be a scalar. Alpha is a scalar. Okay, therefore you can define V, which is z bar by alpha, okay, is the required generalized eigenvector. Okay, of index 2. So you see, it's actually coming from the Cayley-Hamilton theorem, because the kernel here has, this is the important thing. This is the important thing. And that this step is basically says that This basically says that the geometric multiplicity is strictly less than algebraic multiplicity. If it is not, then you won't be able to do this. Okay. So corresponding to, therefore, now the justification for the existence of generalized eigenvector is clear. Okay. So what is the use of these generalized eigenvectors? Okay. Now let's move on to the next question of what is the way that can we write this exponential for a matrix, exponential function, the same lines as exponential of ax or exponential of a into t. Okay, so let me again write on the definition. A 2 by 2. Yes. Yes.
A minus lambda I z bar equal to alpha I sir कैसे हुआ?
This one, because alpha
A minus lambda.
Yeah, because you see that a minus lambda I, this is a vector, right? So this is some vector which belongs to a minus lambda I, right? It is in the eigenspace. A minus lambda I times that vector is 0, means that that vector belongs to the eigenspace of lambda. So if I call this one as V, not V, W, that means A
But
minus lambda I.
सर आइगन स्पेस सब लैम्डा में से तब बिलोंग करेगा ना जब a minus lambda I z bar equal to 0 होगा ना.
That's what I am saying here. Listen to me first. Call this one what is in the bracket here. Call that what is there in the bracket as W. Okay. So what does the W satisfy from this equation itself? A minus lambda I W is 0. What does that mean?
Yes, sir.
That means W belongs to the eigenspace of lambda. W is an eigenvector. That's what it means.
Yes, sir.
That's what I wrote, eigenspace of lambda. So what is eigenspace of lambda? That means it is nothing but alpha times u. U is the eigenvector. So alpha is a scalar. So it is in the eigenspace means alpha u. Is this clear? Is this clear?
Yes, sir. Yeah.
So I call 2 by 2 Jordan block. Okay. So you can say associated with the eigenvalue. Lambda. Okay. Is we write this as lambda 1 0 lambda. So that is called the Jordan. So what is the idea is here. Just recall what happens in case of diagonalizable matrices. Suppose A is similar to diagonalizable matrix, then you write something like this, right? Where D consists of only the eigenvalues, and you know what are all the matrices which has this property. Okay. All the symmetric matrices, normal matrices. So if A is a normal matrix, then it is diagonalizable. That means you collect all its eigenvectors and then put them in the columns of P. And if you want a unitary matrix, then you orthogonalize them using the Smith orthogonalization process. Then you get this P to be unitary matrix. So this is also known as unitary orthogonalization, unitary diagonalization. Right. So you have such a thing. If A is a diagonalizable matrix, right, then you have P into D into P inverse. Right. So if I'm looking at the system, which is say x prime equals to ax. I'm looking at the system x prime equals to x. Then I know that A is nothing but P D P inverse into X. Okay. So multiply both sides by P inverse. So I get P inverse X prime equals to D P inverse into X. Okay. So if P is a constant matrix, we are talking about the constant matrices only. So P will be a constant matrix. Therefore, what we have here is this is nothing but P inverse X and its derivative is D into P inverse X. So that is we have y prime equals to dy, where y is P inverse X. If you see what is this y prime equals to dy, how does this look like as a system? As a system, it looks like y1 prime, y2 prime, like this. And you have a diagonal matrix, lambda 1, then 0, 0, y1, y2. So what are the equations here? The equations here is, first equation is y1 prime equals to lambda 1 y1, y2 prime equals to lambda 2 y2. So that means each one is an exponential function. You have solutions. So that is the y here. Each one is going to look like e power lambda 1t, right? E power lambda 1t, y1, y2 is e power lambda 2t, like this. Okay, so this one you can write it as e power t into t. Just annotation. I don't want to write it, say that use the thing as exponential of a matrix, but as a notation. Okay, so what we are doing this in the from the differential equations point of view here is you have a system of equations. We are converting that into a system of decoupled equations. That means decoupled means there is no coupling here. y1 prime just depends on y1 only. y2 prime depends on y2 only. So if the matrix A is a diagonalizable matrix, then we know that the system is decoupled. The system is completely decoupled. Okay, so if it is not a diagonalizable matrix, then definitely you will have the geometric multiplicity less than the algebraic multiplicity, right? And therefore you have a situation where this doesn't appear. Then what we are planning to now show is that for any matrix, okay, you will have the Jordan form, and this D is replaced by J for any matrix. And then how the solutions of J looks like. Suppose if I the aim is to show this. Aim is to show that A is nothing but E JP, where J is a Jordan form. Okay. And you can do the same calculations what we did earlier. Multiply by P inverse into X prime is going to be, okay, J into P inverse X. So this is now Y prime, looks like J into Y, where Y is P inverse X prime. So what's the advantage of this system? This system now, you see, it is say for example 2 by 2 system. How does it look like? Y1 prime, Y2 prime, and this side the matrix is going to be lambda 1 0 lambda and y1 y2. So that is what y1 prime is lambda y1 plus y2 and y2 prime is lambda y2. So first you solve this and put it here, and then you can solve like that. Right? So it looks so simple from the back substitution point of view. So you can just back substitute to get a solution, complete solution. And such a thing, such an equation plays a very important role in writing the solution like this. Right? And if I can write the solution completely in the form, then earlier I called it as e power dt. So I can call it as e power gt. Okay. So once if I know what is e power gt, then I write what is e power at. So from here we write e power at. How do you write that? You have a system, you have a method here. Right? So if y solves this equation, then x solves this. Y solves this, then this x solves this one. X prime equals to x. So that's the whole idea. So what is that helping us? What is that our aim is? That's what I recalled here. Just said what is the Jordan block associated to an eigenvalue lambda. So this is the. So let me continue. So what is that we are showing is that if lambda is a repeated eigenvalue with geometric multiplicity less than algebraic multiplicity, right? So this is theorem. Say take n equals to 2. If lambda is repeated, and geometric multiplicity is strictly less than algebraic multiplicity. Okay. Then we know that there are generalized eigenvectors, right? And let u and v be generalized eigenvectors of index 1 and 2 respectively. Okay. Then A is equals to P J P inverse, where P is U, the matrix with U and V as columns. Matrix with U and V as columns. What are U and V? U and V are generalized eigenvectors. U and V are generalized eigenvectors. So, since I am taking n equals to 2, the most of these proofs are, I mean, of course, even for general n, you can write down the same thing. None of these steps are difficult to write for general n. But only thing is that in general n, you will have some eigenvalues are repeated and some eigenvalues are not repeated. So I will tell you a general statement of a theorem, how for n by n it looks like. So a minus lambda I into u equals to 0, okay. And a minus lambda I into v equals to. Okay. So let us take the matrix P, which is uv, that is u1, u2, v1, v2. Okay, and j we already said lambda 1, 0, lambda. So now we use the fact that AV, okay, so AV is nothing but A minus lambda I plus lambda I into V. Okay, so this is A minus lambda I V plus lambda V. So A minus lambda I V is nothing but U plus lambda. Okay. Also, we have the AU equals to lambda. So call this as 1, this is 2. And we can use this 1 and 2 to write what is A into the matrix B. You can, because it's a 2 by 2 matrix, you can directly write also. Otherwise, if you understand how the matrices are multiplied, so this is A to U B, which is AU AB. Okay, it is nothing but lambda U. This is U plus lambda. This is what we have. A. On the other side, you look at what is PJ. PJ, okay, just multiply these two equations, these two matrices P and J. You get lambda U1, okay, U1 plus lambda U2, U1 plus lambda V1, lambda U2 and U2 plus lambda V2. And this is a matrix which is actually lambda U and U plus lambda. See that both these things are same. Therefore, AP equals to PJ, and that's the claim that we have. A equals to PJ P inverse. Okay. So all these things one can do for an n by n matrix if there is only one eigenvalue for an n by n matrix, and algebraic multiplicity is n and geometric multiplicity is going to be 1. The same proof works. In general, one can write the following. If you have an n by n matrix with real eigenvalues, A is going to be similar to a matrix in the Jordan canonical form. So what is the Jordan canonical form? Is a matrix which you can write as several Jordan blocks, J1, J2, like this, Jn. Okay, so each J1 is a block, is a Jordan block. So Jordan block, okay, it can be just eigenvalue, because if it is not repeated, some of them can be just equal to eigenvalues. If they are repeated, then the Jordan blocks will look like what I said, the off diagonals will have ones. In case of 3 by 3 matrix also you can write, right? So in case of repeated eigenvalues with algebraic multiplicity greater than geometric multiplicity, so just look at how many times it is repeated. You can write, say for example, of order 3, you can write like this. So if it is repeated 3 times, okay, so then you will have the Jordan block like this. So the off diagonal will have ones. Right? So like this you can write what the Jordan blocks are depending on the times that is repeated. Okay, so this is and the matrix A can be written as P, J, P inverse. Okay. And the idea is that the system of equations that you write, either they will be, if it is say for lambda 10, if there is only lambda 10 is different from other eigenvalues, then lambda 10 will have an eigenvector. So that 10th equation will be decoupled. Okay, where you have the Jordan form, they will be coupled, but still you can write the solution through the back substitution process. Okay, so I will stop it here. I will continue with the next lecture, the other 2 questions that I asked. Any questions you have, you can ask me now.
Yes, sir.
Huh?
सर वेरी फर्स्ट जो आपने थ्योरम करवाई थी V1 V2 Vn आर जनरलाइज्ड आइगन वेक्टर ऑफ n क्रॉस n मैट्रिक्स देन दे आर Li, ओके।
या
सो हमने उसका प्रूफ n = 2 लेके चले थे। तो जब हम मतलब मेरा डाउट बस इतना सा है कि इंडेक्स की जब हम बात करी थी तो उसको रिस्पेक्टिवली 1 और 2 ही क्यों लिया, मतलब इन पर्टिकुलर?
I mean, somewhere respectively 1 and 2 लेना ही पड़ेगा. I have to tell, no, the U is of index 1 and V of index 2. Otherwise, you can take V2. It's only n equals to 2, so you can take V of index 1 and U of index 2, just to fix it.
That means सर मतलब किसी 2 वेक्टर्स का इंडेक्स सेम नहीं हो सकता है क्या?
2 vectors का index n कैसे हो सकता है? In case of n equals to 2 means I have a 2 by 2 matrix, right?
Yes, sir.
Then how there can be more than 2 linearly independent eigenvectors and linearly independent set? Can have only 2, no?
Yes, sir.
So I'm doing for
If
the
it,
n equals to 2 case. So I said there are, I'm taking two eigenvectors and generalized eigenvectors. They are linearly independent. How can there be third vector which is linearly independent?
yes, yes, clear. But अगर n equals to more than 2 होता है तो there is a possibility कि दो वेक्टर का इंडेक्स सेम हो सकता है.
दो वेक्टर का इंडेक्स, I mean, this is what I told you. Suppose you have a 10 by 10 matrix. Okay, you have the eigenvalues. Okay, look at the eigenvalues. So one eigenvalue is repeated say 5 times. One eigenvalue is repeated 5 times, and it has say only 2 linearly independent eigenvectors. So we have to find other 3 which are generalized eigenvectors.
Okay, sir.
Yeah. So in that case, what I said, what you saw, the 2 eigenvectors which corresponding to linearly independent corresponding to 1 of index 1, right? If the geometric multiplicity is same as algebraic multiplicity, even though the eigenvalue is repeated, that means what? That means you have 2 linearly independent eigenvectors. So both of them are of index 1. Both of them are of index 1. But from 2 onwards, it's not possible. That's how we define, right? From 2 onwards, it's not possible.
Yes, sir.
Because we define it as a least number k.
Yes, I got it.
Okay. These abstract things looks so beautiful to study, and once if you understand this, how this linear algebra or the matrix theory is actually helping us in decoupling the system of differential equations, you can actually write the solution of differential equation in a very compact form, and we understand very clearly how the solutions are coming. Okay, and how the structure of the solution looks like in a very compact form. It gives a clear picture of, that's the beauty of abstractness. Okay. Okay.
Yes, sir. Thank you, sir.